we just derived the formula. What formula? Fourier integral, right? Yeah. So now let's look at the Fourier integral, this formula. First, we apply the Fourier integral to represent a simple function. So what's that function? Yeah, this simple function. So you can see it's a piecewise constant function. Yeah, 3 pieces. Piece 1, 2, 3. Each piece is a constant. The value, function value is constant. 0, 1, 0. Yeah. So we call it piecewise constant function. Yeah. All right. So there we want to write Fourier integral representation for this function, simple function. Yeah. So we want to see anything special anything interesting we can get. Yeah. All right. So first, let's look at the Fourier integral formula. Yeah. This is Fourier integral formula. Given any function. Yeah. So this function, what is the condition of this function? Right? Yeah. So the first thing we need to think about, what is the condition of this function? Yeah. First thing, we do not require periodic, right? So that's the reason we want to extend the coverage of the function. We don't want to restrict ourselves only on periodic functions. Too restrictive. So we remove that restriction. Second, do we require continuous? No, right? Yeah, we do not. When we write Fourier series representation, continuity is very important. Yeah. Although we do not require the function continuous, but we allow discontinuities, but at the discontinuities, remember last time I talked about, at the beginning, I used 10-something minutes to explain. At the discontinuities, we require some conditions, right? Yeah. All right. So here you can see we haven't seen any condition on this given function f, right? Yeah. So the first question we want to ask ourselves, what is the condition we need on this function? All right? Yeah. Here, because we need to calculate the integral. Although there is a cosine. Cosine function, special cosine function we put here. What do we call it? Remember, we have similar situation before. We have a special name for this kind of function. In Laplace transform, remember that special e function, e to the negative sx. So we have a special name for that function. Anyone remember the name of that function? Here, the similar situation, but here we use the cosine function. Yeah. Kernel. Remember? We call it, this special function we call kernel. I need to write it. I need a cloth to write things. All right. This is the kernel function. Okay? All right. Yeah. So, although we have this special kernel function used in this integral, but can you imagine some reasonable condition we need to apply on this f function? Okay, yeah. So here, let me give it to you. Yeah. Many discontinuities with side limits, right? Yeah. Last time, that kind of condition. Here, the condition is this. Absolute value of f of x, then we take integral, must be less than 50. Okay? Yeah, we call integrable. Okay? Yeah, so this condition, F, integrable. Integrable condition, right? Then, if we have this integral condition, then we know when we do this integral operation here, so both sides, yeah, for capital A function, capital B function, we can always get valid function, right? Capital A of W, capital B of W. Because when f is integrable, then these two functions are always valid functions. Now, because for integration, there is also convergence issue, right? Convergence. If f is integrable, then these two integrals are guaranteed to be convergent. Convergent. Okay? Yeah. Yeah. So now we know with this condition, and this condition is very easy to get satisfied in the real world situation. Yeah. Because weaker than continuous, right? Continuity. Yeah. Much weaker than the continuous requirement. Yeah. All right. Now, under this understanding, let's calculate capital A function, capital B function, yeah, here, right? Yeah. So piecewise constant. So the integral is very simple. Yeah. You know. Yeah. So A function. Then B function. Look at the B function. It is 0 because we can easily see it's reasonable. The B function must be 0 because this F function is an even function, right? Yeah. It's a perfect even function, and the sine function is an odd function. Even function times odd functions, also odd function. The integral of an odd function on a symmetric interval, right? Yeah. Positive half, negative half, same, symmetric. Yeah. On that symmetric interval, its integral must be 0. Yeah. All right. Then B sine part. So in this final representation, the sine function part gone. Yeah. So we only have one cosine part function. Okay? So we get this new representation. This f function can be represented in this new integral form. Yeah. First, it is non-trivial, right? How can people imagine that simple piecewise constant function can be represented in this special integral? Yeah. How to see it, right? Yeah. How to see it? Yeah. Second, yeah, that means it gives us some new properties. Yeah. Second thing is we plug in some function value and see what can we get. Yeah. So some interesting function value here we want to plug in. Yeah. When x equals 0, how about that? The function value at this 0 point, it is 1. So the left-hand side, it is 1. And the right-hand side is some special integral. Yeah? So 0 times w cosine of 0 is 1. So it's an integral from 0 to infinity sine of w over w. And the value of this integral is pi over 2. How can we see it? Right? Yeah? It's very hard to calculate the integral sine function over w. Yeah? Right? How to see it? Yeah? So here you can see, we can see this representation is useful, right? Yeah. At least this new representation can expose some interesting properties, right? Right? So that's something we like. Yeah? Expose some nice hidden properties. Think about that. Yeah. If someone asks you to prove it, how can you prove it? Right? Yeah. Or people want to verify it. Yeah. How to do it? Yeah. Yeah. So here we apply the Fourier integral representation. We can prove it. All right? Yeah. So that's the, first thing. Yeah. Second thing, yeah. Here I want to do summary. Because here why we do this, right? Yeah. So in this summary, I want to explain why we do things like this. Yeah. So our goal is problem solving, right? Yeah. So what do we want to do? So here, what we are doing here, we want to see if it is useful in problem solving. Okay? Yeah. So that is important. Yeah. All right. So let me explain. Yeah. So because we want to do some high level understanding, yeah, problem solving. Yeah. All right. Yeah. Here, we have a function, right? So basically here you can see we are studying a function. Yeah. So regarding a function, yeah, so there are two parts correlated. Yeah. Yeah. So one aspect, the content of the function. The content of the function, the definition of the function. Okay? Yeah. Also, yeah, so the understanding of this content part, yeah, corresponds to the data content, right? So what's the content? The data content. Yeah. That's our data. We work on our data. We are given. That's the, initial data, input data we need to work on to solve the real world problem. So that's the function. Okay, all right. But other than the content, there are another aspect, yeah, also important. That's the form of the function. A function can take various forms, right? Various forms. All right? Yeah? Yeah. The content can never change, right? For a given function, the content part must be fixed. Yeah. Yeah. That's the given data. Okay? Yeah. Yeah. So we should not change it. Yeah. We should not alter it, right? Yeah. The content part. But for the form part, we have freedom to choose different forms, right? Yeah. That's the representation. Yeah. We have various representations for a given function. Yeah. Which representation is better? It is closely related to the given problem, right? Yeah. For some of the problems, this special type of representations work better. For some other different problems, other different representations work better. Yeah. All right. So here we want to look at the various forms of for function representation. Yeah. All right. All right. Yeah. So I will give you some summary on the function forms. All right. Yeah. Yeah. So the first one, there is a infinite series form, right? infinite series form. Okay? Yeah? So people represent a given function in a form of infinite series. Okay? All right? But for the infinite series, we have learned Fourier series, right? Yeah. We can write as a Fourier series. Yeah. Fourier series. Oh. All right, that's one. And another commonly used series representation, power series. Yeah, this will be our next topic, power series representation. Okay, yeah. Yeah. Sometimes we need to use power series representation. Okay, yeah. Another important tool in problem solving. Okay, all right. Yeah, definitely there are other series, yeah, but relatively less popular. Yeah, other, series representations. Yeah, yeah, yeah. Here I can give you one special. Yeah, yeah, because that's the, people need to use some higher level knowledge. Yeah. Series called a spline series. Yeah. Actually, spline functions is very useful in industry. Yeah. Yeah. Spline series. What is spline? Spline functions. Piecewise polynomials. Spline means piecewise polynomials. Sorry. Polynomials. That's the meaning of spline. Okay? Spline. Yeah. So in industry, a lot of software, developed using the spline tools. Yeah. Automobile industry, yeah. Airplane design, the shape, yeah. Typically using the spline functions. Yeah. And machinery, the parts, different shapes, how to quickly generate, special shapes of various parts of machinery. Spline functions. Most popular tools, spline functions. Yeah. Yeah, but for this class, we cannot cover that part. Yeah. It should be very, very useful for your engineering students. Yeah. Here, I just mentioned it. Yeah. All right. Yeah, so the infinite series representation form, or other representation, yeah, so integral representation. Integral, so here, yeah, you see, cosine integral, sine integral, right? Yeah, integral representation. Yeah, and last time I mentioned integral just has some similarity comparing with summation, right? Yeah. So here, integration and summation has some similarity. Can you see that? Yeah. Yeah. Integral, summation, what kind of similarity? Yeah, because, one way to see the similarity, accumulation, right? Summation, you accumulate all the terms. Yeah. Integral, you accumulate pieces, the areas of the pieces, right? Yeah. The curve, the area below that curve, but that's the, accumulate the area of many small pieces. Yeah, similarity. You look at from this point of view. All right. But they are also different. So look at the difference between integration and summation. One important difference. Yeah. When you look at the form of the integral, it's in a form, continuous form, right? Yeah. Continuous. Function value changes smoothly, right? Yeah. Smoothly from beginning to end. So continuous as a whole thing. Yeah. So integral has a property, it's a continuous version. Continuous version. Okay? Yeah. So we use the continuity property of a function. Yeah. That aspect. Summation, term by term. Okay? Term by term. So when you accumulate terms, you look at the partial sum. Last time we used partial sum to approximate infinite series. Every time you want to improve the approximation precision, you increase the number of terms, right? One by one. One by one. You look at the object you are working on, that's the discrete way, right? Yeah. Every time you add one term, two terms, three terms, that's the discrete way to work on the functions. Yeah. One is a continuous way, another is a discrete way. How about that? Okay? Yeah. That kind of understanding. Yeah. All right. Yeah. But still more here. Yeah. All right. These two forms, this one, they both, yeah, so these two, both on the time domain. Time domain. What's that? Yeah. Spatial. Yeah. Here, x actually is the spatial domain. Spatial domain or time domain. Time domain, that's the t. Okay. So we use variable t. Time domain. When we use variable x, it's the spatial domain. Okay. Yeah. So time or spatial. All right. Yeah. So these two cases, we work on both time or spatial domain. Okay? Yeah. Then there is another special type of function representation on a different domain. Okay? All right. So that's by the transform. Transform. We represent function through transforms. Okay? Transforms. So we have learned Laplace transform, right? Yeah. Laplace transform. Yeah, so let me just write the name. I do not need to write the transform word. Laplace transform, next. Yeah. So the part A of module 5, the topic is Fourier transform. So we will learn Fourier transform, this part. Yeah. All right? And these two transforms, it's not in time domain or spatial domain. Yeah. So Laplace work in the S domain, right? Yeah. So, sometimes people call frequency domain. Frequency domain. You just know it's a different domain. Okay? Yeah. Completely different domain. So you work on a completely different domain. All right. What's the benefit? Yeah, here, I give you a summary of the typical different forms for a function. You can see so many different forms. What's the benefit in problem solving? Yeah. A lot of benefit. benefits in problem solving. Okay. Level abstract view of the benefits. Yeah. Yeah. Because when we do not see the real world problems, we cannot get into much specific. Yeah. So in the high level, yeah, the benefits, because with different forms, different representations for functions, we can view, we can understand functions from different angles. Yeah. Why more angles, more views for functions can benefit us more? Why? Because when you have many angles to understand functions, you can see more properties. Now, more properties for that functions. Yeah. Because if you only use one angle to look at those functions, many properties are hidden through that angle, through that particular angle. Hidden. So they exist, but in a hidden way. So this angle cannot expose those hidden properties. Yeah. All right? Then you change the angles. Then suddenly, this angle, suddenly it exposes some special property. So you can catch that property, you can apply that property to solve the real world problems. So that's the basic idea. Yeah. So why people develop so many different representations for functions. Now we have so many different angles to look at the same function. Yeah. We hope one of the special angles can expose some critical properties. Then we apply those properties, we solve real world problems. Yeah, so that's the general thinking. Yeah. Yeah. All right. Yeah. So based on that, yeah, so we can also use this as the motivation for us to study different representations for functions. Yeah. So now we need to learn the Fourier transform representation. Represented in different domain this time. Okay? In the frequency domain. Yeah? Yeah. It's like you go to different world, right? So time domain, spatial domain, that's our current world. Okay? Current world. The system. We are familiar with system. All right? Yeah. Now, in order to expose more special properties, there is another powerful way to look at this world. Yeah, the same thing in this world, but we transform it to a different world. Frequency domain, we can treat it as another world. All right? Yeah? Okay? Yeah? So, yeah. Yeah. Something like, in our current, environment, in the news, So, typically we view the surrounding objects on Earth, right? So we know how to view. Suddenly now, yeah, people, the astronauts get to the moon, so they view things from moon, from that different world, right? Yeah, a lot of things look differently, quite different. Things like that, okay? Yeah, we get to a different domain to study the same the content does not change. So after Fourier transform, after a Laplace transform, the data, the intrinsic property of the data has no change, right? Yeah, because we can transform, we can recover the original data. No loss, no gain, yeah, because exactly the same data. There is no loss and no gain. not get more data. Same amount of data. Yeah. Yeah. So that's the, some general understanding as the motivation for our next topic. All right. Next topic I want to talk about, D.4. Fourier cosine integral, Fourier sine integral. Yeah. All right. The special case for even odd functions. Yeah. All right. Because, so this is the original formulas for Fourier integrals for general functions. Yeah. But when we look at the even odd functions, the formula can be simplified. Yeah. So that's pretty easy. Yeah. For the even function, we know the sine part is gone, right? Yeah. For odd function, the cosine part is gone, right? Yeah. So for the Fourier cosine integral, where f is an even function, we just have this cosine component. All right. Yeah. For the Fourier sine integral, when you apply, you need to make sure you apply it on the odd function. Otherwise, it's a wrong application. Okay? Yeah. Make sure the function is right. Yeah. Then you have a sine component this time. Yeah. All right. Yeah. Yeah. All right. Yeah. All right. Just two special cases. Yeah. All right. Next, another topic, our last topic of Module 4, Part D. Yeah. All right. Oh, yeah. Before we do that, we do a simple special example, Laplace integral. Yeah. So we want to see anything special we can get. But when we do Laplace integral, we want to connect it to Fourier cosine integrals and Fourier sine integrals. These two ways. Okay? Yeah. Fourier cosine integral, Fourier sine integral. All right? Yeah. But the question is, we know this function is not an odd function, right? It's neither even function nor odd function. Yeah. Okay? Yeah? But how can you apply Fourier cosine integral for non-even function? How can you apply Fourier sine integral representation for a non-odd function, right? Yeah. So here, remember, actually we can. Yeah. So we can. So here, yeah. Through this example, you will see, although we require the Fourier sine integral, cosine integral for special even odd functions, but in the real-world applications, actually we can do more than that. Yeah. So we look at from this example, we can see we can do more. The application situation could be more general than even function, odd function. Too restrictive. Yeah. Most functions are not even function, odd functions. Yeah. Like this one, E function, not even, not. All right. But remember, so from last lecture, we learned a special method to extend our function. Yeah. That's what we call function extension. We call it half-range extension. Still remember a little bit? Half-range extension. We can do half-range extension. There is an even extension and an odd extension, right? Yeah. So here, this function we treat. Can we understand this function as a half-range function? Yeah. So this function is defined, although it's not odd, but when we consider x positive, k positive, we treat this function as a half-range part of a function. Then we can do even extension or odd extension. How about that? Right? Yeah? Then we can apply cosine integral version, sine integral version, right? Yeah, so here, let me draw the picture a little bit for even extension, odd extension. For even extension, look at the graph. X positive, k positive, it's a decreasing function, right? Yeah. So when x equals 0, it is 1. Okay? 1 is its highest point, right? Yeah. Starting from this value 1, then it's decreasing, right? And when x goes to infinity, it's 0. The limit is 0. Okay? All right. Can we do even extension like that? Okay? Yeah. Symmetric. Okay? Flip along the y-axis. Okay? Yeah. Reflection. Yeah. All right? That's the even extension of this function. Yeah. Similarly, odd extension. So you can imagine odd extension, right? Yeah. Yeah. So the shape, so odd extension. See? So when we do even extension, we can apply Fourier cosine integral. When we apply the odd extension, we can use the Fourier sine integral representation, right? Yeah. But we only consider the piece on the positive x-axis, positive half x-axis. All right? Yeah? Yeah. So now, you should feel comfortable when you apply Fourier cosine integral and Fourier sine integral. Yeah? So we do extensions. Yeah. All right. Yeah. So let's do the work. Yeah. Yeah. All right. I wrote that formula. All right. Yeah. So the formula I put there when we do Fourier cosine. Yeah. Yeah. So here. Yeah. All right. Yeah. Here, the first half, we do the Fourier cosine integral representation. So we need to calculate this integral for a function. Okay. All right. So after some, calculation, we get the result. Yeah. A function. All right. Then, so our f function, you can see you get a Fourier cosine integral representation. Yeah. On the positive half axis. Yeah. All right. Yeah. You can write a different form. You can see this represents non-trivial, right? It's not easy to get this representation. Non-trivial. All right. Then, for the Fourier cosine integral, this time we do odd extension. So we can do it. Okay? Yeah. All right. So then we do the calculation. All right. Yeah. So we get a result. So the final representation, you can see this time we get a completely different representation. Two different so same function. Here, look at the right-hand side. Right-hand side, exactly the same function. Oh, yeah, k, yeah. Anyway, yeah. But the left-hand side, you can see, quite different. Yeah, quite different. Yeah. All right. Yeah. Yeah, so that's we finished this topic. Yeah, yeah. All right, so integral. So this example tells us one thing. Yeah. Tell us one thing. Yeah. For the given function, yeah, through these two extensions, yeah, so we can apply Fourier cosine integral, Fourier sine integral. Yeah. So don't worry, the general functions may not be even function, odd functions. Yeah. Yeah. So this tells us the Fourier cosine sine integrals actually can be applied in most of the cases. Yeah. All right. Next, our last topic, D.5, numerical integrals. Yeah. So let me explain. Yeah. This last topic, so why it is important, yeah, I want to talk about. Yeah. All right. So let me give you a brief introduction for this last topic. So the numerical methods in this class. So far at this point, we haven't done numerical methods. No, we haven't done. So all the methods, the traditional analytical methods. So far, what we are doing, analytical methods, not numerical methods. Yeah, it's like, two different areas, but numerical methods are very important for engineering students, for engineering people, because when you solve real-world problems, most of the time you use numerical methods, more practical. Yeah. Analytical methods, although they work, but the percentage when they work is relatively small. The large percentage computation work, you need to do the numerical computation. Yeah. All right. So here I want to talk about numerical integrals as a small short introduction, but in Module 5, I want to talk about numerical solutions for ODEs and PDEs. Yeah. Just some general ideas. Yeah. Yeah. All right. Numerical integral. So why numerical integrals? Yeah. So you will see in the real world situation, first, numerical integration is a process approximating a definite integral using well-chosen sums of function values. Yeah. So this sentence tells you how to calculate numerical integration. Yeah. All right. Let's look at a simple example. For this integral, definite integral from a to b, the function e to the negative x squared over 2. So this function, Gaussian, right? Yeah, people call it Gaussian function. The bell shape, Gaussian, symmetric. Yeah. So this function is a famous function, very famous. Okay. Yeah. Yeah. It's an even function, right? Symmetric about the y-axis. Yeah. So if I draw the graph, people also call it the bell shape, like that. Okay? Yeah. Bell shape. Gaussian. Okay? Yeah. So people refer to it. Gaussian. All right? Yeah. Yeah. So very famous. Yeah, very useful. But the problem is how to calculate this integral, right? Yeah. It is very hard, on an interval from A to B. Yeah. The function looks not that complicated, right? Because there is a square, so it's very hard. If we remove that square, that's very easy, right? But there is a square. Okay. Yeah. How you handle that square? Yeah, it's too hard. Okay. Yeah. So in the real world situations, you have a lot of chances. You need to work on integrals like this one. Yeah. You have some nice functions. But when you need to calculate integral, extremely hard. When we use our typical methods, we cannot do it. Nobody can do it. No existing formulas, methods, substitution. Yeah, people try all those methods. None of them works. Yeah. And the percentage in the real world is very high. A situation like this, the percentage, very, very high. Okay? So we can, in this situation, we can only consider numerical approximation. Yeah, numerical, that's approximation. Yeah. So now, the first, so we need to get ourselves feel comfortable on numerical methods to solve real-world problems. Yeah. So let's start with numerical calculation of integrals here. All right. There are several methods. Yeah. Here, I want to give you some ideas. Although this topic actually, for many students, so when you take higher level calculus, so Calc 2, Calc 3, high level calculus, so you may already, you have learned this topic. Yeah. So here I want to use it as an introduction for our numeric method topic. Yeah. All right. For the first method, we want to do approximation of this integral. We use the trapezoid rule. What's the trapezoid rule? All right. When we calculate the integral, that's the area under the curve, right? Area on the curve. But we approximate the area under the curve piece by piece, but each piece has the shape, trapezoid shape. Okay? Trapezoid shape, so we need to apply the area formula of the trapezoid. Okay? Yeah. So you know the formula of trapezoid area. Yeah. All right. So when we do that, it's an approximation, right? Yeah, because not a perfect fit. Okay. Yeah. So when we make that trapezoid smaller and smaller, then we can approximate original integral better and better. Yeah. All right. So nth trapezoidal approximation was capital N. Capital N, we divide the given interval from A to B by n line segments. Equally spaced, n equally spaced line segments. That's capital N. So we use that capital N to control the number of terms, and at the same time, we control the approximation error. The larger that capital N, the smaller the approximation error. So there is an error. Yeah. So you cannot avoid the error. Yeah. But we want to control the error. Okay? Yeah. All right. So let's look at the formula. Yeah. The formula approximate equal based on the trapezoid rule, calculated area. So this is the formula. Delta x, the length of each small line segment. Okay? Yeah. So when we divide the given interval, AB from A to B. Yeah. So equally spaced interval. Yeah. So delta x times the y values. Yeah. Summation. Yeah. So you can use a program. Okay? When you do the calculation, especially when the capital N value is relatively large. Yeah. So you don't want to do hand calculating, right? Yeah. So people write a program, a Python program, for loop. Yeah. All right. So you can do the calculation. All right. Delta x, the length of the interval b minus a divided by capital N. Yeah. Delta x. There, yi, the function value at those, evenly divided the points of the interval. Yeah. Then, so this summation, we use the notation capital T sub n. Yeah. Trapezoid, so we use T sub n. Okay? Represent this whole sum, yeah, in this form. All right. Yeah. All right. Then we can consider the error. Yeah. When we use this formula, how large is the error? Yeah, that is important. We need to know when we estimate, when we do approximation on a given interval, how large is the error term? Yeah. We want to know that, the precision. Yeah. Precision of the approximation. Yeah. That's important. Yeah. So we want to, if the error is acceptable or not. In the real world application, yeah, you need to, after you provide the final answer, yeah, people want to know how good is the approximation, right? Yeah. So if you have the error estimate, yeah, the error is controlled in a very small range, so then people will feel confident. Oh, this solution is acceptable. Yeah, things like that. Yeah. All right, let's take a 10-something minutes break. After you come back, let's look at the error part. Yeah. That's very important, the error.